This is a homemade material that can provide as much cooling as twice its weight in ice. It has more thermal mass than 15 times its weight in concrete. This type of material can keep you cool on a hot day. It provides warmth in cold weather, and it can even regulate the temperature of an entire building. Hi, I'm Ben. Thanks for being here with me. I've been working hard for the past few weeks testing this and other temperature-regulating compounds to come up with high-performance recipes that would be easy for you to make at home. This one in particular I'm really excited about. I think it may even save lives. So, let's learn about phase change materials. The most common example of a PCM, that is, a phase change material, is ice. Ice absorbs energy in the process of melting, changing into liquid water. That, of course, is the phase change, solid to liquid, or the reverse, liquid to solid. One of the coolest things about a phase change material is that you would imagine that this piece of ice sitting on my hand would be getting warmer as it melts. But no, it stays at exactly the same temperature for the entire time that it's melting. The temperature is locked in until enough energy has been sucked from my hand that there's no more ice left. It's fairly easy to recognize that an ice cube is absorbing heat from your hand in the process of turning back into liquid. But it's maybe less intuitive to notice how much heat water releases when it freezes into ice. Here I've supercooled the contents of this bottle, which means I've lowered the temperature of the liquid to the point where it should be frozen. But ice is a crystal, and crystals need a place to start growing from. The technical term is a nucleation site. This could be a speck of dust, or a disturbance like slapping this bottle. In this case, I'll pour out the liquid onto a dish with one small frozen crystal in the center. The liquid, which remember is below its freezing point, instantly turns into ice on contact. You can do this, by the way, with ordinary bottled water. Put the bottles on their side in a freezer and wait about an hour before trying this. Most will begin to freeze, but if you're lucky, some will still be completely liquid, which indicates supercooling. Look at this effect now through a thermal camera. When the ice forms, amazingly, it releases heat, becoming much warmer than the liquid still in the bottle. This once again is a demonstration of how much energy is involved in a phase change, in this case from liquid into solid. When the supercooled liquid begins to freeze, it launches up in temperature until once again it locks in at its very specific freezing point. It can't become any warmer than the freezing point because that would require enough energy to melt the ice that just formed. To put into perspective how much energy we're talking about, melting a given quantity of ice requires the same amount of energy as to then take that recently thawed liquid and raise its temperature almost 80% of the way to its boiling point. That is a lot of energy just to melt a piece of ice. Okay, ice is cool stuff. The point I'm getting at is that a phase change can be very useful for either absorbing or releasing an enormous amount of thermal energy, and it doesn't require a large change in temperature to do so. This glowing hot piece of steel contains a lot of thermal energy, but it required a very hot flame to charge it up, so to speak. An appropriately made phase change material could store just as much energy pound for pound as a glowing hot piece of steel, but it could do so at a temperature low enough to hold in my hand. Ice does this at 0 degrees Celsius, 32 Fahrenheit, requiring 334 joules of energy per gram to be either released or absorbed to change its phase. It's a thermal battery, and making a custom PCM allows us to pick and choose other temperatures which will make the battery more effective for different conditions. Two parallel purposes which have stood out among the many requests I've received over the years is to come up with a way for paramedics to cool down victims of heat stroke, and to come up with a better emergency fire shelter material which could be used to protect woodland firefighters if they're about to be overwhelmed by the flames. A low-temperature PCM could be ideal for both cases. Ice is already a low-temp PCM, but it's actually too cold to be very useful, because on a hot day without access to a freezer, it's very likely to melt, to lose its cold charge before you actually need it. A PCM with a melting point somewhere between ice and room temperature will last much longer, and could even be recharged with ordinary air conditioning in a vehicle. This is one such PCM. The primary ingredient in this mixture is sodium sulfate, an inexpensive and non-toxic salt, which can be purchased on Amazon or eBay for a few dollars per pound. Mixing this with just enough boiling water to fully dissolve it produces a PCM which has a freezing point around 95 degrees Fahrenheit, 35 C. That might actually be cold enough to allow someone to survive in a fire shelter, but it's not cooling anyone down from heat stroke. We'll come back to this because a high melting point PCM has its own variety of uses, but that's not what we're looking for right now. To lower the melting point, we need to mix this with another salt. In this case, ordinary table salt. By the way, we'll be looking at other PCMs that can be made purely from items that can be found in a grocery store. But this recipe using sodium sulfate is so good that I think it's worth making first. I'll throw the recipe on screen here. This will make a phase change material with a melting point of about 18 degrees C, 65 Fahrenheit. Actually, this will have multiple melting points, which makes it even more useful, but we can ignore that for now. Fortunately, this mixture does not require super precise measurements, so we can use the most basic measuring cups and kitchen tools to make it. I'll start with 5 cups of water. That's 1.2 liters added to this pot, and then we'll turn on the burner to get it heated up. The powdered ingredients start with 1 cup. That's a 240 milliliter scoop of sodium sulfate added to the water. Next comes 1/4 cup, 60 milliliters of table salt, sodium chloride. These are stirred until the water begins to slightly boil, and probably they will not fully dissolve. And that's good because we want the water to be completely saturated with as much salt as it can take. If all of the salt does completely dissolve, we'll actually need to add more sodium sulfate until there's at least a trace that doesn't go away with more heat and stirring. If you're feeling ambitious and there seems to be a lot of undissolved salt, you can add excess water a little at a time to keep absorbing more of it until there's only a small trace left. But otherwise, the main part of this recipe is finished. This liquid is now a working PCM. One problem with using a salt-based PCM in its pure liquid state is that as crystals form, they tend to settle to the bottom of whatever container they're in, and the salt doesn't necessarily distribute evenly again when the crystals eventually melt, and that causes issues. This can be fixed by adding a gelling or thickening agent to the mixture, and there's lots of good options for this. CMC, carboxymethylcellulose, is the most common one used in commercial products like toothpaste. But for something you can find in a grocery store, xanthan gum is a great option. This is a bacteria-derived gelling agent, and if we add 4 teaspoons or 20 milliliters to this mixture and let it simmer for a few more minutes, it will thicken up and prevent the formation of large crystals which are likely to sink, and also keep the whole solution a lot more stable. Actually, if we keep boiling this for about a half hour, it will turn into something like Jell-O when it cools, which actually works even better. This is amazing stuff. An 18C melting point means that you can freeze this with easily accessible geothermal energy. What I mean is that this will freeze on the floor of a basement. Only right near the equator are ground temperatures more than 18C, 65 Fahrenheit. For most of the world, with access to a fairly deep hole in the ground, this is an ice pack that you can recharge for free. Actually, you could do it for free close to the equator also. You just have to look to the sky instead of to the ground. Check out my radiative sky cooling series to learn more on that point. With an appropriate cooling paint that can send its heat off into space, these could recharge anywhere in the world without electricity. You might say that 18C isn't that cold for an ice pack, but that's the point. 18C, which again is 65F, is just cold enough to pull heat from your body on a hot day. It's like the water temp in a cold swimming pool. It doesn't cool you down as fast as ordinary ice, but because of the smaller difference between this material's melting temp and your body or air temp, it melts much more slowly. We just made enough of this PCM to fill half a dozen of these sandwich-sized bags to make ice packs, each of which I've found to last many hours for personal cooling as I've been testing them over the last few weeks. Reusable silicone sandwich bags are the best option to make these. They're less likely to break than these single-use bags. When I started running some tests on this PCM, I was surprised by a few properties I did not expect. First of all, if you cool it to 18°C, it stays there for many hours, as expected. But that feels very strange. It's like the sensation of flipping over to the cold side of a pillow. You can imagine that sensation of cold fabric, and this feels similar, a little bit colder, but you're used to things at that temperature getting warmer as you touch them. Your brain expects this to do the same, but it just stays at that temperature. It actually would make an awesome lining in a pillow. If anyone wants to hire me to consult on that, I'd be happy to help. More surprising than the sensation of touching this PCM is that it seems to outperform ice, and not only at room temperature like I expected. It starts freezing at 18°C, but there are multiple stages of freezing that occur in this mixture if you keep cooling it further. The first is at the top of this curve, which you can see in a graph I recorded during the process of cooling the PCM in my home freezer. You can see that it's supercooled before actually forming the first crystals, and then it shoots back up to that 18°C freezing point. And here is where I don't actually know what's going on, because instead of staying level at one given temperature, it seems to have a progressively colder freezing point for whatever unfrozen liquid remains in the container. It's a slow ramp downwards, which I did not expect. The other line, by the way, is an equivalent amount of water being frozen into ice, and you can see that the temp levels out right at water's freezing point, which is what I also expected for my PCM to do at 18°C. And that's not what we get. The initial stage is at 18°C, and a lot of energy is clearly stored there. But the ramp downward after that point is slower than the water which is cooling beside it. That indicates that there's probably still a phase change occurring, seemingly with a progressively colder freezing point as it carries on. Once the PCM and ice were both frozen, I continued tracking their temperature as I warmed them up, side by side, in a circulating hot water bath. This is a serious torture test. Look at how quickly the ice warms up, with barely a pause at its melting point. Meanwhile, my PCM actually started a few degrees warmer than the ice, but instantly shot below it at the start of the test, and stayed below the ice temp long after the ice lost all of its cooling potential. So not only can this provide cooling at 18°C, but if you do have something like a freezer, or ironically a cooler full of ice, to lower this PCM's temperature further, more of it keeps freezing. And then it provides even better, longer-lasting, low-temp cooling than ice. This is very weird. Every paper and journal article I could find agrees that sodium sulfate-based PCMs only store about 2/3 the energy of ice. And yet I've double, triple, 4 times over checked these results. Every time this mixture beats ice. I even did a rough experiment during a Patreon live stream to check the total cooling capacity per gram, where ice had all the advantages in the experimental setup to come out on top. This stuff still measured as having twice the cooling capacity. You've seen how I do things. My methods do not always yield perfectly accurate test results.
Oh, you guys.
But I'm at least convinced that this is really useful stuff. So knowing that this can be used to hold a temperature of 18°C or cooled even further, there are some awesome applications. First of all, small PCM packs like this are very useful as is, especially if paired with a vest that's normally meant to carry ordinary ice packs and keep them pressed against your skin in hot weather. You can find a vest like this, again, on Amazon or eBay. They're often used by anyone that needs to work in a non-air-conditioned environment. The straps on the side of a vest like this are key. You need the PCM packs pressed tight against you, or else the cooling will mostly be lost into the air. For the purpose of cooling someone down in the case of heat stroke, we might want something a little bigger than this. Here's my first attempt at making a larger PCM cooling blanket. To make this, I mixed up a batch of the PCM liquid and then soaked it into a towel. You should wait for it to cool down first, and definitely wear rubber gloves to do this in case it's still hotter than you expect.
Ow, ow, ow. Yikes, yeah, it's hot.
For this first version, I sealed the PCM soaked towel into a heavy garbage bag. I got some tips after posting an earlier video about making solar-powered weather balloons that you can heat seal plastic by melting the edges together with an open flame, if you use a metal ruler to prevent the heat from going too far. This did work, but I think it would take more practice to avoid catching the edge on fire. A better option I discovered is to simply lay out the towel in a large vacuum seal bag. Close it and then squeeze the air out. No heat sealing required. These are awesome, and not just for emergency use. Actually, my favorite application was an accidental discovery. This is the perfect cooling seat cushion. I've spent hours sitting on this thing in a lawn chair, pretending it was important research for this video. Everyone needs a PCM seat cushion, especially if you're something like a delivery driver in a vehicle with inadequate air conditioning. This is luxury, and it stays cold for a really long time. When I'm working on these projects, I've found that I become more confident in my ability to sit down and learn a brand new topic the more that I try. I don't try very hard to learn new things, I just try to learn a little bit about something I'm interested in almost every day. And that's what eventually turns into these videos. Brilliant.org is the sponsor for this one. They've been my sponsor, I think, for more than 5 years, providing thousands of hands-on interactive lessons in math, data analysis, programming, and AI, with a particular focus on helping give you the tools needed to feel confident in your ability to learn anything. You'll definitely find with any course on Brilliant that your problem-solving skills and critical thinking are put to the test in a really good way, building knowledge in bite-sized pieces that fit together perfectly to teach you a brand new subject. It's a great way to get into the habit of learning new things every day. I think you'll find that it's also a much more satisfying habit than mindless scrolling. One course that you might start with is Brilliant's series on LLMs, which covers the technology behind AI programs like ChatGPT. I really enjoyed that one, and it helped me to understand a lot more about how AI works. You can try everything Brilliant has to offer for free for 30 days using my link, brilliant.org/Nighthawk, and that will also get you 20% off an annual premium subscription. This definitely would help cool down a person with heat stroke, especially if it's kept in a cooler with ice at 0°C to give it that initial boost. I'm not sure if it's better to be covered with this like a blanket or to lay on it like a cooling mat. If someone made a larger version, you could wrap it fully around a person and do both. In terms of applying PCM technology to a fire shelter, the limiting factor there, I think, would be weight. Currently, fire shelters are made from lightweight fiber insulation with a reflective outer layer. Here is an old generation shelter, and the new ones are also approximately this size. It would add a lot of weight to soak the fiber with a liquid PCM, and while it would absorb a lot of extra heat, I'm not sure if it would be worth the potential loss of insulation. I might do more experiments with this at a later time, because one option that might make these shelters work a lot better is to coat them in an expanding fireproof paint, which we learned about in an earlier project. You'll have to wait for a future video to see how that turns out. Well, with that, we've explored our first PCM, which operates at a temperature ideally suited for personal cooling. This is what you might call the tip of the iceberg. PCMs have many other uses at a variety of temperatures. One of those is temperature regulation of a building. Here is a PCM pack with a melting point around 85 degrees Fahrenheit, 29 degrees C. This was made in a similar way to the cooling blanket. I took some shop rags and soaked them in the PCM solution, and then placed them into a plastic bag. The rags help keep the liquid distributed evenly so that it doesn't pool in the bottom if you hold this pack upright. This allowed me to make a panel, which can be attached to the underside of the roof of my shed. During the daytime, my roof becomes extremely warm even on a cool day because shingles absorb a lot of heat. The PCM pack produces a noticeable cold spot as it absorbs the excess heat in the process of melting, and this reduces the air temperature of the building. Where a PCM pack has an advantage over traditional insulation is that when the sun goes down and the roof begins to cool, now the panel reverses functions. It remains warm, keeping the building's temperature from dropping at night. It smooths out the up and down cycles which would normally be experienced by an off-grid building, both heating and cooling it as needed. We looked at one high-temp PCM which would work for this purpose already. Pure sodium sulfate without any additional table salt would work well for temperature regulating a building, having a transition temp of 95F 35C. The air temp in a building is not going to get as warm as this transition temp, by the way. It will be a balance between the ground temp, which is cooling it from the floor, and the PCM, which is warming it from above. 35C at the roof should leave the air a pretty comfortable temperature at ground level. This pack, however, was not made with sodium sulfate. This is a purely grocery store PCM made from calcium chloride, purchased in the form of sidewalk salt. This container was about $7 for 8 pounds of calcium chloride from my local grocery store. If you are really serious about using this for a large project, you can buy it from a bulk supplier for less than $200 per ton, although delivery might be significantly more than that. Preparing this for use is essentially the same process as with sodium sulfate. Add 1 1/4 cups, or 300 milliliters of water to a pan. Then add 4 cups, or 1,000 milliliters of calcium chloride, which should be approximately 1,000 grams. Once the water is simmering and the pellets are mostly dissolved, 1 teaspoon, or 5 mils of xanthan gum will increase the viscosity and prevent the crystals from settling. And that's it. This is a finished PCM with a transition temperature of 85F 29C. This will easily absorb into things like shop rags or cellulose insulation, to then be sealed into bags and used to create these panels which can regulate the temperature of a building. Another excellent use for this type of PCM is to increase the performance of solar panels. A solar panel is most efficient right around room temperature and can lose as much as 0.5% of its efficiency for every degree Celsius that it warms in the sun. With one of these sandwiched against the back, we could limit the temperature of the panel by absorbing excess heat. This excess heat would then be later passively released into the coldness of night. Whew, extremely hot. Using a high-temp PCM for these purposes does have a few caveats which we should talk about. The first is that this solution of calcium chloride especially is corrosive to metal, and so it has to be well sealed in order to prevent leaks. Sodium sulfate is much less corrosive, so it would be a better choice in that respect. For regulating the temperature of a building with PCMs, the primary concern is humidity. Many modern types of construction actually depend on large swings in temperature in order to allow the building to breathe and drive off humidity during the day. With a PCM-regulated building, you don't get the temperature swings, and so in damp weather, you might actually have to run a dehumidifier in the living space or in a building's attic to accomplish the same effect. Generally, that will still save a lot in electricity compared to running an air conditioner, so PCMs used in this way can be very worthwhile, as long as you know how to deal with the side effects that might occur in high humidity climates. One other high-temp PCM that many of you might be familiar with is sodium acetate trihydrate. This actually has a very high melting point of 140 Fahrenheit, 58C, making it a good option for personal heating in the form of these little hand warmers, or for collecting solar heat to release at a later time. The most interesting thing about sodium acetate is an extreme ability to supercool, far below its freezing point. These little packets are currently at room temp, but if I snap a little metal disc inside, it creates a nucleation point for crystal growth, and suddenly the packet shoots straight up to 140 degrees. A few years ago, I tried making these packets myself for another video which was never published. My conclusion was that if you want one of these PCM hand warmers, just buy one. They're not worth the difficulty in making them. Search for sodium acetate hand warmers online and you'll find many options in different sizes and shapes. It is tempting to try to make these yourself because sodium acetate is a really easy chemical to make. In fact, most of you will have already made it unknowingly by reacting vinegar with baking soda. Yeah, your science fair volcano was bubbling out a high-performance PCM as a byproduct. The difficulty in making sodium acetate with vinegar and baking soda is that it takes a lot of vinegar, and the end result is not likely to be pure enough to actually stay liquid like this once it's been supercooled. It's also more dangerous than you would expect. Spilling liquid sodium acetate on myself is one of the scariest experiences I've ever had while working on one of these projects. It's already hot from being prepared in a pan and boiling off the excess water. But once it touches your skin, it sticks and starts to crystallize, shooting up to that 140-degree freezing point. Fortunately, that was not hot enough to cause my skin to seriously burn, but it was hot enough for the sensation of it sticking to my hand and suddenly increasing in temperature instead of decreasing like everything else I've ever spilled on myself. That is an unexpected and terrifying sensation. As useful as sodium acetate is as a high-temp PCM, I would not make it again myself without a very good reason to do so. These little hand warmers, which you recharge by leaving them in a pot of boiling water, are a nice product and a great demonstration of PCM technology. There's many other options beyond what I've discussed so far. This video topic was inspired by my previous video involving molten wax for waterproofing fabric. Hydrocarbon-based PCMs, like molten wax, can be tuned to operate at a variety of temperatures with additives like oil. However, doing so lowers their heat-carrying capacity. The best wax-based PCMs use very pure forms of wax, with melting points determined by their particular chemical structure. Unfortunately, it's difficult for the average person to purchase these very specially refined types of wax. The salt and water-based PCMs, which we've explored here, have some real advantages anyway, such as low cost and zero flammability. If you'd like to see more from my channel, I've recently started occasionally live streaming as I'm working on these projects, and those streams are posted to Patreon. That gives you the opportunity to ask questions or make comments about my projects as I'm actually doing them. If you'd like to directly help with what I'm doing here and my efforts to make this kind of science accessible to the average person, please do support me on Patreon if you have the ability to do so. If not, no worries. Thank you simply for being here and for watching this video. I read all of the comments, so leave me one below. Thank you so much for watching. I'll see you next time.